In this video, I want to go into more detail about the thermal and mechanical units involved in the Carnot process for power generation. Let me just draw the process and then we'll zoom in on the individual units. Okay, first of all, I'm going to have a fluid, usually water in the case of power generation, go into a boiler. And I burn fuel to evaporate the water. So it's going to go from liquid to vapor. And I could call that QB for the Q boiler, which is what I called it in previous videos, but it's more often called QH or Q hot. We'll talk about the abstract Carnot process later, so you can see what is really meant by Q hot. Then we take the steam and we put it into a turbine, and we get work out of it. I label it as negative because work that comes out of my system by the convention we use in my class is negative work. We desire negative work or work extracted. What we get out of the turbine is a low pressure gas, which we then condense in a condenser. And it's necessary to extract QC. We haven't yet explained why that's necessary. We will. And we go from state 3 to 4. And then we need to close the loop with a pump. So with the pump, we put in work, and that brings us back to state 1. So notice that I have two types of units. I'm going to say this is a thermal unit, and this is also a thermal unit. And the pump and turbine are mechanical units. The purpose of a thermal unit is to exchange heat, and the purpose of a mechanical unit is to either put in work or extract work. Let's talk first about thermal units. Okay, so the purpose is heat exchange. So the simple energy balance is delta H equals Q. Remember, well, if you took my class, you'll remember when we discussed the energy balance for flow systems, the reason we put delta H and not delta U into that equation is because delta H contains the work necessary to flow the fluid through the system. So that's not the work we're talking about. We balance delta H with Q and W so that we can have separate terms for shaft work, which we would either put in a pump or extract. But this is a thermal unit, so we don't intend to do either in this case. So the ideal behavior for a thermal unit is going to be constant pressure. We ignore any pressure required to get the system through, and infinitesimal driving forces. So the driving force that is most important is the temperature. So T is approximately TH or TC. TH in the case of the boiler, TC in the case of the condenser. And the idea is that heat exchange requires as small as possible of a temperature difference between the surrounding and the system. This is kind of a natural, well, I don't know, maybe not natural, but if we use a two-phase system, notice that the boiler would have a liquid going in and a vapor going out. So if we assume this is a saturated liquid and this is a saturated vapor, or somewhere in between, it's kind of natural for the temperature to be pinned at the boiling temperature for that particular pressure. So the constant pressure is fairly natural for you working in a two-phase system. But that isn't strictly a requirement for a boiler. Okay, so the real world, I mean, when we talk about ideal, that implies something about the real world. So in real world, pressure is not really constant, and the temperature on either side is not necessarily the same, right? But when you start getting finite temperature differences and finite pressure differences, that's when you depart from the reversibility, or at least reversible systems. Let me draw this way. So say I have a hot reservoir at TH. I would be putting QH into the boiler. That could be the burning fuel. We have water going in, and we have steam going out. And ideally, what we mean is the T boiler would equal TH. In the case of the condenser, I would have steam going in and water going out. And I need to remove heat in order for that to happen, in order to close the loop of the power cycle. And I would need to remove heat into some cold reservoir I'm going to call TC. So let's look at the energy balances. Okay, so H out minus H in. This is for the boiler. I should make that more clear. So this is for the boiler. Is going to equal QH. So that means that delta H across the boiler is going to equal QH, and the system is not designed to put in work or extract work beyond the work necessary to flow the fluid through the unit. The condenser energy balance looks very similar. H out minus H in equals negative QC. In other words, there's a loss of energy due to heat removal. Delta H would equal negative QC. The W of the condenser would be 0. Again, that is easier to do, or at least easier to approximate in the real world if you have a two-phase system at a constant pressure. Let's look at entropy balances. So the S out minus, I did it again, I forgot, didn't mention what I'm balancing, boiler. So S out minus Sn would equal QH over TH. That means that the delta S of the surroundings, the hot reservoir is considered part of the surroundings. It would actually be equal and opposite. So again, a reversible process. There's no change in the delta S of the universe, so the delta S of the system has to match the delta S of the surroundings. So this is the hot reservoir. And you get it by burning fuel. In reality, the process of burning is probably going to generate entropy, but we are not considering that here. We're just assuming the hot reservoir is at TH somehow. Now the condenser looks very similar, except it's removing heat, which means that the entropy of the system, the working fluid, is going to go down. So this is the system, and so is this. The system is the working fluid, the water. And the delta S of the surroundings, which is the cold reservoir, wherever you're rejecting the heat, maybe the atmosphere, is going to equal and opposite. In this case, the cold reservoir is going to gain entropy because of the heat transfer. And now notice that it's important that the system and the surroundings have the same temperature where the heat exchange occurs. Otherwise, it's not a reversible process. Of course, in reality, those temperatures won't be exactly the same. For example, in order to get heat into your boiler at a rate that you'd probably be satisfied with, you probably need the hot reservoir to actually be above or higher in temperature than your working fluid. But of course, we're looking here at the reversible limit. Okay, so let's talk about mechanical units. So the purpose is to perform work or extract work. In the case of the pump, you are putting work into the system. In the case of the turbine, you are allowing the system to do work that you might use to charge a battery or something. Ideal behavior is that this too would be at constant entropy. Adiabatic reversible process. To be honest, I don't know how to design a pump or a turbine to be reversible. I'm a chemical engineer, not a mechanical engineer, but I'm told that mechanical engineers know how to make something that comes close to reversible, or at least can be modeled as reversible and then adjusted with an efficiency term I'm about to talk about. So the real world, now remember, adiabatic means no heat transfer. So the ideal mechanical unit does not transfer heat, it only performs or extracts work. So in the real world, you have irreversibility caused by heat generation say friction. I think I'm going to put an EG there just in case there are other ways of generating heat. I don't think there are in this kind of unit. Or exchange. Say it takes too long for the fluid to go through the pump or the turbine, and so it may exchange heat in the atmosphere. What we do in this case is we say that whoever built the pump or turbine gives us an efficiency. This is different from the efficiency of the whole process. This is referring to the efficiency of the mechanical unit. And so this refers to, for a turbine, this is the shaft work that you get out of the turbine divided by the shaft work that you would get in the isentropic limit. So if it's a 60% efficient turbine, what you can do is estimate how much work you would get out in a constant entropy mechanical process and then take 60% of that. In the case of a pump, it's similar but not exactly the same, because you are not trying to get work out, you're trying to put work in. So reality means that WS isentropic is actually going to be less than what you end up having to put into the pump to get it to the initial and final state that you desire, or get it to the final state from the initial state. So let's look at energy and enthalpy balances. Let's first do the pump. So I start with a low pressure fluid. Usually when we say pump, we're referring to a pump that is designed to work on liquids. Pumps that are designed to work on vapors are actually called compressors, although they are still pumps, but they're designed very differently, and the impression I get is that a compressor is more expensive than a pump. I have no actual experience with either. So energy and entropy balances. So in the case of a pump, H out minus H in is the shaft work of the pump. No heat exchange for an adiabatic pump. S out minus S in equals 0, which is also equal to delta S of the surroundings in the isentropic case. Now you might ask, in the case of the less than perfect efficient pump, I'm sorry, that's actually here. Well, you will actually have to account for the fact that you put in more work than is accounted for in the delta H, right? And so there probably would be some heat exchange in that case. So there would be Q in a real pump. Okay, so in the case of a turbine, it looks very similar, except you're going the other direction. You're going to get work of the turbine out, and I suppose I could call that negative work because it's coming out of the system. So by dropping the pressure, you're spinning a turbine and extracting work. So H out minus H in equals minus shaft work of the turbine. S out minus S in equals 0. and that's the delta S of the surroundings in the ideal case. In the next video, we're going to put it together and analyze the overall efficiency of a Carnot process.